Thanks, y'all. So yeah, I'm going to talk about scaling Python for machine learning. Specifically, I'm going to talk about going beyond data parallelism. I think a lot of us are probably familiar with data parallelism, but if you're not, that's okay. We'll go into it a little bit. And there will be a lot of pictures of dogs because I miss my dog. This is Professor Timbit, and don't actually remember this dog's name, not my dog. But Professor Timbit will feature prominently throughout, so if you zone out, just look at the dog, he's cute. Okay, so I guess we've already sort of met me, but we're gonna go on a super fun motorcycle adventure together, also known as the photos that I have on my phone are of motorcycles and my dog. We're going to talk about what data parallelism is, why it might not be enough for all of our use cases. We're going to look at a use case which isn't exactly machine learning, but I think it does a really good job of illustrating one of the alternatives to data parallelism, which is actors. And we'll also talk about why you should definitely come and work for my employer, because they like it when I say that, apparently. Okay, yeah. So I'm Holden. I mostly work on Spark for open source. I'm on the PMC, which is like tenure, except you don't guarantee that you get paid. You just guarantee that you get work. So it's like the shitty part of tenure. It's okay. I've written a few books around mostly data processing stuff. I think they're pretty cool, but I'm obviously pretty biased. If you're interested, you should follow me on the social media. I live stream a lot of my mistakes. So if you ever like feeling down about yourself and you're like, I really want to watch someone else struggle with incredibly basic tasks that she's done several times before, come and check out my live streams and you can feel good about yourself. And sometimes, you know, we do interesting things that actually works, but most of the time it's just failing in public together. So, you know, keep it exciting. Yeah, rockin'. So yeah, in addition to who I am professionally, I'm trans, queer, Canadian, and part of the broader leather community. These things are not directly related to software in any particular way. When I talk to JVM people, I say there's no magic decoder ring for JVM stack traces that they give to Canadians. Similarly, we don't have any magic secret GDB Canadian-only version for understanding Python core dumps. There's nothing magical about this. But I think, especially because we're talking about machine learning, it's important for us to try and have more diverse communities involved in building our machine learning tools and models, because otherwise we'll just end up reinforcing all of the world's existing badness, but by putting it inside of a magical black box that we can't introspect. And so if when you are, you know, meeting with your team and you realize like, hey, we all went to UC Berkeley class of 2020 and someone from 2019, you know, that's cool. That might not be a diverse enough crew to really be building good machine learning tools. I make this joke slightly in jest, but a lot of these tools are built by class of 2019 and 2018, UC Berkeley. Great folks, but you know, it's good to have some people with different experiences and backgrounds in the room. So I also have a bunch of like more relevant biases. I'm used to working with really large scale data sets. If you are working with smaller scale data sets, the things that I'm gonna say may not be relevant to you. You should be aware of that. These, you know, I've mostly worked at the platform level for the past while, which means I'm a little bit out of touch with people who accomplish actual tasks. I make software to help other people make software. And so as such, I get distracted sometimes by shiny new things. And you may like look at these things and say like, Holden, this is a great shiny new abstraction. It's not for me. And you should not feel like you have to listen to me. Also, I think these tools are pretty cool. I've contributed to them. There are other tools as well. And there is that bias where when we've worked on tools, we can think they work well. In my case, I don't think they work well. I think they're all garbage, but they're garbage that I'm familiar with, and you might be familiar with other garbage, and you should use that. Or if you're familiar with things that work, that's amazing. That's great. Never heard of it. Super excited. Also, I think functional programming is cool. You can see that I had a weird upbringing, because my idea of what is cool is largely formed from 1990s Genko genes and functional programming. Growing up next door to an engineer in the 90s gives you all kinds of weird vibes. But if you don't think functional programming is cool, that's okay. Some of the things that I'm going to say today, you're probably going to just be like, not for me, once again, and that's okay, right? Like maybe you just really love mutating state with blocks in Zookeeper, and that's, you do you, not for me, but whatever. These are all fine. Okay, so what is data parallelism, and why are we going to go beyond it? So the classic version of data parallelism is we split up our data into a bunch of things called partitions. Often this will be keyed. We'll have like key value pairs, but not always. We could just have thousands and thousands of like rows, and they're just there, and we split them up. Generally speaking then, we apply the same logic, either row-wise or partition-wise, but we generally apply the same function to all of our data. And then at some point, we'll recombine the partitions in some way. We'll do a shuffle, or we'll do a reduce or something, because it turns out that we can't always just apply the same logic to each partition. But most of our work in data parallelism is sort of around this idea of we have many, many copies or different variations of a thing, and we want to do the same thing to that. And that's great. I also have this fantastic PDF that's in progress called Distributed Computing for Kids, which is focused around data parallelism. So if this 10-second refresher isn't enough for you, that's okay. You should definitely check out Distributed Computing for Kids to get sort of the vibe of how to do Apache Spark programming in Python for ages, I would say 6 and up, but people tell me that I'm crazy. So maybe more like 12 and up, whatever. Okay, so when is this not enough, right? So here we see Professor Timbit and an empty bowl of food. Clearly, this is not enough. We have made a mistake. There should be more food. But there's a bunch of things where data parallelism just isn't really well suited to helping us scale, right? Model weights, if you saw the reinforcement learning talk yesterday by Dean, was amazing. Data parallelism, not great for reinforcement learning, right? We have all kinds of state that we need to keep track of, and data parallelism just really isn't designed to keep track of a lot of state for us. The other one is, our tasks are a bit like heavier weight in sort of data parallelism world. And so if we've got lots of tiny, tiny little tasks, generally speaking, the schedulers for data parallelism aren't going to excel there. Non-uniform tasks, this one is really the kicker. Yeah, we could, of course, write a map expression, which will just have 200 if-else conditions inside of it to apply different logic to each element. It's probably kind of ugly, right? We probably don't want to do it. You could, but really, if you've got non-uniform tasks, data parallelism, well, you could probably force it to do some of what you want to do. It's not going to be the nice, happy abstraction that you want. So what are we going to do instead? So we've got choices, right? And here we see that Professor Timbit has chosen the cream cheese over the kibble. Very smart. Similarly, we're going to try and choose our version of the cream cheese instead of the kibble. So to be clear, because of my bias, I'm used to working with really large data sets, and so I tend to skip over local solutions, right? If solutions are only going to work on one computer, they're probably not going to work for $glorious employer. But they may work for your $glorious employer. And so locally, you can use things like joblib and multiprocessing, and then you can do shared state with locks. And I mean, that doesn't sound fun, but you can do it, and it'll probably be a lot better. Alternatively, in the distributed world, we can do distributed tasks, and we can do distributed actors. How many people are familiar with the actor model? Ooh, so few people. This is exciting. I'm really excited. And for those of you who are familiar, well, my apologies for later, but this is fun. Okay. And we can also, of course, do that same locks and shared memory approach. It's just going to be a lot slower because we're going to have to use distributed locks like Zookeeper and all that stuff. And we can also use databases. They're not bad. They're pretty good for tracking state, but there's some downsides, of course. Okay. So why is this hard, right? Why is moving beyond data parallelism hard? So fundamentally, our problems here come down to the fact that we're working with distributed computing, and as Leslie Lamport says, a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. And we see this in Spark, we see this in pretty much everything, Dask, Ray. And the problem is the computers are like, they're the computers that I have in my little rack in the data center. They're garbage. I bought them on eBay. And you might be going like, Holden, I run in the cloud. My computers are, of course, the finest, best computers. They're never going to fail. I've got bad news for you. They're going to fail too. They might not have been bought on eBay, but they were certainly put together by someone who has not slept anywhere near as much as they should, thanks to the magic of capitalism. Okay, I can't joke too hard about capitalism because I enjoy eating. Okay, yeah, so what do our distributed tasks look like? Now, this is a bit of a stretch because this is a picture at Disneyland, but it's a picture at Disneyland Japan. So we can think of our distributed tasks as like, we send someone to Disneyland, and then we send someone else to Disneyland Japan, and we both ask them to go and get us some Mickey Mouse ears, right? And because of this, we can achieve a greater level of parallelism than we could if we only sent people to Disneyland, California, because we've got 2 Disneylands to load balance over. Okay, there's like one person that likes Disneyland, or at least is willing to pretend. Okay, the other one is functions with decorators, or in this case, we can wear our Mickey Mouse ears, or our Pooh Bear hats, also acquired at Disneyland. So what we do is we take a thing and we put a decorator on it. Ooh, decorator, magical, at Dask delayed. So this is our hat or Mickey Mouse ears that we put on top of our remote function, and now our remote function can get scheduled anywhere in our cluster. And normally, we'll get the same result regardless of where we're running. Here, intentionally, I've written it so that we get different results depending on where we are running, so that we can actually verify that, like, yes, this is running on a different computer, so we can tell the difference between Disneyland California and Disneyland Japan. This is very important. The Mickey Mouse ears generally look the same, but if you pay attention, the tags are a little bit different. And that's essentially what we're doing here with socket get hostname, is we're checking to see if we're in California or Japan. Okay, and similarly, the other toolkit that we can use to do this is Ray, and we can see very different. Instead of Dask delayed, it's Ray remote. These things are definitely different, 100%, 100%. So let's talk about how they are different. So Dask and Ray are both frameworks to allow us to go sort of beyond data parallelism, and they both give us this sort of delayed/remote concept, and they're very similar. Dask delayed defaults to lazy computation. So what I like to think of is Dask as me as a teenager who, when I ask them to go and take the garbage out, they don't. They say they did, but they don't. And it's only once I go and I check and I see that the garbage is there that they actually go around to taking the garbage out. Ray remote, on the other hand, is like, I want to say like 10-year-old me who still had hopes and dreams, who, when you asked to take the garbage out, would of course take the garbage out right away. And then when you go to check, yes, the garbage is not there. It's great. Now, functionally, these don't make a huge difference, right? Lazy versus eager. With lazy evaluation, sometimes Dask can combine a bunch of work together, which is nice. And if you're used to working with Spark, you'll see, or other data parallel things, lazy is a pretty common sort of approach used in the data parallel world to allow for chaining of tasks. You can also chain tasks with Ray Remote, but it's more of a sort of schedule flow rather than a strict saving of computation time. Another minor difference is Dask uses a centralized scheduler and Ray uses a bottom-up quasi-distributed scheduler. And if you're going like, I don't know what the difference is between these two, that's pretty normal and fine. Essentially, the downside of Dask here is that if we schedule like, I don't know, an imperial, I probably shouldn't swear, a very large number of tasks, everything does get routed through this one central computer for scheduling purposes. And that's, not ideal at super large scales. On the other hand, it's worked pretty well. Centralized scheduling has many benefits. Ray, on the other hand, allows for computers to schedule their own tasks to a certain degree, and only if it can't be scheduled locally does it get bubbled up to this other scheduler and rerouted out to another computer. And so there's like some minor trade-offs here. Functionally, though, the big difference is lazy versus eager. Okay. So right, how are they the same, right? So they both have distributed and local scheduler options. So this is actually really neat. How many people here have used Apache Spark? Okay, have you used Spark in local mode? Okay, did it go well? Okay, that's a zero out of a small sample, admittedly. So Spark has a local mode, which was a really nice idea, and it didn't work. Fundamentally, you can kind of use it for testing, and that's about it. On the other hand, Dask and Ray both have pretty good local schedulers, which I think is really cool because it means that if you're in sort of the state where, yeah, you know that your company might grow to the point that you want to scale to multiple computers, but you're not there right now, you can still use the frameworks without having to run on a cluster. And so that's kind of cool. Similarly, they both support recursive scheduling. The asterisk means, of course, read a book to find out the many intricate details in cases where this will not work. But this is much nicer because you can have like actual function trees. You can write your code in a much more natural way. And while Dask does default to lazy evaluation, you can force Dask to be eager and get futures out of it in the same way. So they both support futures. Ray doesn't have the equivalent of lazy evaluation, though. So, okay, that's great and all, but we were talking about how what the hard part was is the failure of a computer that we knew nothing about was going to cause our job to fail, right? And so how are we going to get around this problem, right? Because we don't want to depend on that random stack of computers that I happen to have down in Fremont, California. So we handle it by restarting tasks on failure. This is the same sort of approach as Spark. It's not the same approach as Hadoop. Hadoop, the solution is you write out 3 copies of everything and you read it back on failure. Slightly different. The downside here, though, is this means that if we have failure, we just run it again. And if we write a function that's doing something like, say, taking money out of someone's account, they might complain that we take $200 out of their account instead of 5, because we execute this until it finally works. And so this can be not good. And so this is not perfect. You have to make sure that the code that you write is code that can be executed multiple times. And if it's not, then you have to manually add your own checks to make sure that you're not causing excessive withdrawal of money or other things like this. So that's all well and good. Also, interestingly, much like Boo here, who is a stuffed animal, not an actual live dog, we can dress up just like a person and pretend to be very human. She is Boo of Bark Corp of Delaware. Very legitimate company, I'm assured. Nothing shady, definitely filed their taxes. But we can also make our distributed clusters look kind of like local clusters. And this is really important because we want to use tools like TensorFlow or other machine learning tools that probably weren't written with the idea of running on top of Dask or Ray in mind, but they were written with the idea that like, hey, computers can do more than one thing at a time. And so we kind of want to slip in there and use their existing local parallelism technique and just swap it out with a distributed parallelism technique and hope nothing breaks. In case you can't tell, some things will break, but it does kind of work. And so both Dask and Ray expose a joblib interface, which allows them to sort of pretend to just be one really weird big computer to certain machine learning algorithms. And underneath the hood, they use these tasks to accomplish that. And that's kind of, I think it's kind of neat. So essentially they put on glasses and go up to TensorFlow and say, hello, I am 200 computers. I mean one computer with 200 cores. No questions. And then things go predictably. Okay. Now, for the 5 people who had used Spark, oof, I should really know that. I've worked on that project for 10 years. Yes, Spark does have tasks, right? And technically, we could maybe sort of accomplish the same thing in Spark, but in practice, Spark does not expose tasks. It simply uses this task concept to achieve data parallelism, and Spark does not trust us with the tasks, and it will not let us make our own tasks. It's very sad. Maybe that will change, but honestly, I don't think so. I think more likely, we'll just use Ray or Dask instead. Okay, cool. And now we're going to talk about actors. And here we can see, continuing the Disneyland tradition. I think this is Disneyland, California, not Japan, but my photos are not super organized. But actors sort of go beyond the basic task principle. So with tasks, if we have state, right, we're kind of up a creek. Because these are just getting scheduled randomly somewhere on our cluster. And if we try and change something, the next task that gets run, it's not going to necessarily see the variables that we changed in our previous task. Whereas actors get scheduled in a more persistent way, and we can use this to track state. And we pass messages between the actors. Here we can see the passing of the message. We've got the Disney signature book being passed from actor 1 to actor 2 to request actor 2's signature, who will then return the signature. Sorry, Disneyland. Okay, really though, the important thing here is what we do is each actor is responsible for some state, and they communicate with other actors, but other actors cannot directly change the state that is inside of that actor, right? And this allows us to avoid the problem of having to deal with distributed locks because we only have one person who is responsible for some state, and provided they're processing the messages serially, we're okay. Everything is fine. That is also foreshadowing to the time when everything is not fine, and we will get there soon. Okay, so for our actor example, we're going to use one of my many side projects, which is a satellite communication device called Space Beaver. I'm Canadian, and satellite, space, beaver. Okay, I thought it was funny. So what we do is we make this satellite client. We have to put in a bunch of annoying setup work. Don't worry about it. You can find the sort of boilerplate code online. I'll link to it in a little bit. But then we can write our super happy fun main function here. And so this run function is actually just really terrible polling. And this is because I love hardware engineers, they're amazing. When they write software, they really love polling interfaces. And so to pull messages off of the satellite devices, we end up sort of just polling and waiting for a message to become available because I don't have a way to subscribe for notifications. And so this is kind of funky, and we end up putting this polling function inside of an actor so that it's running consistently in one place, and we can track our state. And so this function just talks to itself, which is, I mean, like me in high school. But it's important. Actors can have their own state, and they don't necessarily only have to respond to external events. They can have polling and other things happening. Similarly, here we have an actual function which we expect another actor to call. This is the send message function. This doesn't super have to be inside of an actor. We could maybe put this as a remote function, but once again, because hardware developers writing software, they get really annoyed when I try and send too many messages to their backend at the same time. So I used an actor here so that we would know that we were only sending a fixed number of messages to the backend rather than just randomly scheduling them anywhere in our cluster. And so here we take a bunch of things and we base64 encode it because, hey, if we don't, it makes the computer sad. Okay, next sad thing. Right, okay, and then this is where we take our client base and we turn it into an actor. And if you'll look at this, you can see the decorator that we're using, or the hat that we've put on our function, is pretty much the same thing as before, right? We've got our array remote. The difference here is, that it's on a class instead of a function. And when we put this decorator on a class, array will turn it into an actor for us instead of turning it into a remote task. The other thing here is that we've specified max restarts equals -1. This means that we will restart this an infinite number of times. There are perhaps some problems with this choice, but it's okay, right? It's better than just saying like, oh, there was a problem, I'm just gonna walk away. So okay, this is like one actor, but actor systems generally, you have a bunch of different actors. And so here we can see, like, these are a bunch of actors that are all going to sort of exist and how they're going to talk to each other. We've got a user actor who's responsible for tracking user state. It's going to talk to a database. The other things aren't going to directly talk to that database, so we don't have to worry about locking on it. Satellite actor talks to the user actor, the SMS service. Our mail client, our mail server is separate because computers. And then similarly, we just have one thing talking to the satellites. And that's because when we had two things talking to the satellites, they got confused and told us to go away. And here we can see this diagram redrawn by someone who draws diagrams. And we can see why I should not be allowed to draw diagrams. And so this is what happens when you work with a publisher, is they take this and turn it into this. Ooh, pretty. Thanks, O'Reilly. Yeah. Anyways, same thing, just more readable. Okay. So that's cool to an extent, right? But I've been talking about how we're just going to have one actor responsible for the user information and one actor responsible for talking to the satellite service and so on. And you might be going like, Holden, that sounds great, but I serve ads. And if I had one actor responsible for serving ads, I would have an exciting opportunity to find a new job. And that's a very real possibility, is like we need to scale our actors, because even with having our different pieces distributed, we may need more copies of the individual pieces. And so we'll just do that, right? Yeah, okay. So admittedly, the architecture diagram does start to look a little bit more like one of those Rorschach tests or whatever it is, where you're just like, I see, 6 cows and a cheeseburger. And here it's like, well, I mean, we just made a copy of everything. Everything's fine. No problems. Everything's fine. Everything's fine. Okay. Oh wait. Okay. Yeah. So in practice, right? There is some trickiness that has to happen here, and that is we need to route things somewhat consistently, because otherwise the guarantee that we had, where there was only going to be one actor who was going to be modifying the user state, it's not going to be true anymore, right? Because if we send a message to user actor 1 and user actor 2, if we send messages about the same user to those two separate actors, they might both modify the state, and then bad things will happen. And so similarly to how in data parallelism we have sort of keyed values, we can use the same sort of idea of keying the state. And so user actor 1 will be responsible for users A through J, and user actor 2 will be responsible through J through Z, and similar things like this. And there's little abstractions that you can do. You don't have to manually write your own partitioning here. If you're used to working with Kafka, this should not sound super out of left field. It's a similar idea where we're going to have different partitions, and we're going to have consumers who are responsible for one partition at a time. And this is going to allow us to have them work semi-independently. And that's all kinds of good. Okay, so that's great. We'll scale it. We'll just add more copies of things. Everything's fine. No problems. But that max restarts equals -1 thing. What happens when we restart an actor, right? If we have put all of our state inside of this, if we restart it, some bad things might happen. And that is indeed the case. So while Ray does indeed support restartable actors, it's the kind of support which it's technically there. You just have to do everything yourself. So you get to write your own recovery code, which is great. So if your actor is like the user actor and it's been saving all of its state in a database, that's totally fine, right? All you do is you reestablish your connection to the database. On the other hand, if you've been using a bunch of in-memory stores and the computer it was on fails, you are going to have a bad time. And so you need to write some kind of persistence layer. There are a few different options. My co-author for the Ray book, Boris, has a wonderful example using, I want to say, S3 as sort of the persistence layer. Now, of course, there's sort of a trade-off of do you always want to block all the time until your write has propagated to S3, or do you want to just kind of go, close enough, and just hope. And hopes and dreams, classic software strategy. Speaking of hopes and dreams, you can see the code for hopes and dreams in these two examples. So the message backend example is the one that we looked at with all of those actors. And if you want to see a whole bunch of different variations of applying these patterns, you can look at the scaling Python ML example, and you can see this for both Ray and Dask. And so I think that's cool. The message backend Ray example is, of course, just in Ray, and this is because I'm lazy. Okay, right. So you might be going, Holden, this sounds cool, but you work at Netflix, and last I heard, Netflix is not building a satellite communication device. And to be clear, if they were, they would probably not tell me. But as far as I know, yes, we do not make satellite communication backends at Netflix. We use Ray to train machine learning models. However, it turns out that training machine learning models is kind of complicated, as illustrated by the RLib talk from yesterday. And so if you're interested in applying these techniques to train machine learning models, you should definitely do that, and you should use, I think reinforcement learning is really cool, and the RLib library in Ray is one of the great tools to do it, but there are all kinds of different ones that you can try out. And there's a fantastic blog post on how we are doing this for machine learning at Netflix. The other one is Dask does have actors, right? But we only really did a walkthrough on Ray actors. And you might be wondering to yourself, Holden, why? You already showed me that Dask and Ray are pretty similar for tasks. And that's true. Dask's approach to fault tolerance is hopes and dreams. And that's not the hopes and dreams with the like, you get to write it yourself recovery. This is the like hopes and dreams that our computers just don't break. Also known as no. Yeah. So Dask actor fault tolerance is not ideal. And if you find yourself needing actors, you should probably not be using Dask. And I don't even think the Dask people would be too upset at me saying that. They might not be like super stoked, but like I'm pretty sure I can still get them to have coffee with me sometime. Okay. And you might be going, okay, so you said Spark has tasks inside of it, they're just not exposed. Does Spark have actors inside of it? No. Unless you count code as performance art, which is also known as the like, occasionally someone will enjoy a little bit of the California products and write some very wonderful code that should never be deployed to production. There are some people who have essentially just completely done terrible things to schedule actors using data parallelism, and the fact that they can kind of leave little things running behind inside of the JVM. And so like, yes, technically, but in the way that, yes, technically everything is a Turing machine and nothing is impossible, but please God, don't. Okay. And now a word from my employer. If you've ever said to yourself, I wish I was riding a bus to Los Gatos, and here I am riding a bus to Los Gatos, you should come and work at Netflix. More seriously though, we have roles that are both remote and in person. It is not on my specific team, so you don't have to worry about working with me, but it is on our sister team, so you won't be able to get that far away from me. And I believe the roles are mostly remote friendly, but limited to inside of the US. There are some in Europe and some in Mexico, but I'm less familiar with those teams. Regardless, this website is more up to date than I am. Okay. But most importantly, if you have a corporate credit card, now is the time to purchase several copies of, which one do I make the most money on? I think it's going to be scaling Python with Dask. You should buy several copies. More seriously, if you're interested in these things, I think they're pretty cool books, but I was involved with writing them and I do make money on them, so I'm obviously pretty biased. If you don't have a corporate credit card, don't worry about it. Scaling Python with Dask will be available under a Creative Commons non-commercial license, so you can read it online. I don't think it'll have like the nice O'Reilly graphs because of how the licensing works out. You'll get the kind of shitty graphs that you've seen. My apologies, but it's the free version, so you know. And if you've said to yourself, wow, I hate children. Distributed computing for kids is a great way to introduce children to out-of-memory exceptions. And I encourage you to go, give me your email address, and I will let you know when we finish illustrating book 1. And you too can share the joy of out-of-memory exceptions with children. Okay, I think that's it for my slides. I wanted to save the last like 10-ish minutes for questions, and I think I did that. So does anyone have questions?